Right now, as you settle into the warmth of your evening, held safely in the gravitational embrace of our star, there are worlds drifting through the cosmic dark with no sun to call home. They wander between the stars in eternal night, frozen and alone, following no orbit, bound to no system. These are rogue planets, worlds that have been ejected from their birth systems or formed in isolation, now sailing through the void of interstellar space. They outnumber the stars themselves. For every star you see in the night sky, there might be thousands of these orphaned worlds, invisible and undetectable, passing through the darkness. Perhaps one is passing near our solar system right now, a frozen giant or a small rocky world, coasting silently through the dark, just a few light years away. We would never know. It would be invisible to our telescopes, betrayed only by the slightest gravitational tug on distant stars. If we happen to be looking at exactly the right moment, these homeless worlds challenge everything we thought we knew about planets. They exist without the one thing we assumed all planets needed, a star. Yet they're out there in numbers that stagger the imagination, a vast invisible population of wanderers in the dark between the stars. Tonight we're going to explore these orphan worlds, these cosmic nomads that drift through eternity without ever seeing a sunrise. For most of human history, planets were points of light that wandered among the fixed stars. The word planet comes from the Greek planets, meaning wanderer. But these wanderers were always assumed to wander around something, our sun, other stars, something that anchored them. When we began discovering exoplanets in the 1990s, they all orbited stars. This reinforced our assumption: planets need stars. They form from the leftover material of stellar formation, orbit in the star's gravitational well, and depend on stellar energy for any chance of warmth or life. Our entire model of planetary formation assumed a star at the center. The nebular hypothesis, the idea that solar systems form from collapsing clouds of gas and dust, always placed a star at the heart of the process. Planets were byproducts, accessories, dependent objects that couldn't exist without their stellar parents. This view made intuitive sense. Every planet we knew orbited the sun. When we found planets around other stars, they followed the same pattern. Planets and stars seemed inseparable, like shadows needing light to exist. But there were always troubling hints that our model was incomplete. In the 1990s, astronomers studying star-forming regions noticed something odd. They saw objects that looked like brown dwarfs, failed stars, too small to sustain fusion, but some were even smaller than that. They had masses in the planetary range, yet they floated freely in space, orbiting nothing. These objects were initially dismissed as the smallest possible brown dwarfs. Surely, astronomers thought, there must be a lower limit to what can form independently in space. Planets need stars, it's fundamental. But observations kept finding more of these objects. Some had masses comparable to Jupiter, others were even smaller. They moved through star-forming regions like planets, but they had no stellar companions. They were alone. The real paradigm shift came with improved detection methods. As our telescopes became more sensitive and our techniques more sophisticated, we began detecting objects that couldn't be explained away. Gravitational microlensing. When a massive object passes between us and a distant star, briefly magnifying the star's light, revealed invisible objects with planetary masses drifting through space. These weren't orbiting anything. They were simply wandering. Infrared telescopes detected the faint heat signatures of young planetary mass objects floating freely in star-forming regions. These objects were still warm from their formation, glowing faintly in infrared, but they had no stellar companions. Direct imaging found planetary mass objects so far from any star that no reasonable orbit could explain their positions. They weren't in orbit, they were adrift. The evidence became undeniable. Planets don't need stars. They can exist independently, wandering through interstellar space, bound to nothing but the galaxy's general gravitational field. The most common way rogue planets form is through ejection from normal planetary systems. This process is violent and chaotic. When planetary systems are young, they're crowded and unstable. Multiple giant planets might form in the same system, their orbits crossing and interfering. Gravitational interactions between these planets can be catastrophic. Imagine Jupiter and Saturn engaged in a gravitational dance that becomes increasingly unstable. As they pass close to each other repeatedly, one planet gains energy while the other loses it. Eventually, one planet gains so much energy that it reaches escape velocity, the speed needed to break free from the star's gravity entirely. The ejected planet doesn't just leave its orbit, it leaves the entire system. It becomes a rogue, sailing into interstellar space at speeds of several kilometers per second. Behind it, the remaining planets settle into more stable orbits, having expelled their sibling to achieve stability. Computer simulations suggest this is common. For every planet that remains in a stable orbit, several might be ejected during the system's chaotic youth. Our own solar system was probably born with more planets than the 8 or 9, depending on your stance on Pluto we see today. Where are our missing siblings, wandering the galaxy as rogues? Even more remarkably, some rogue planets never had stars at all. They formed independently, like stars do, but were too small to ignite fusion. In stellar nurseries, vast clouds of gas and dust where stars are born, the same processes that create stars can create planets. When a region of the cloud becomes dense enough, gravity takes over. The cloud fragment collapses, spinning faster as it shrinks, forming a disk of material around a central object. Usually, the central object is massive enough to become a star, but sometimes, the collapsing fragment is small. It might form an object with only a few times Jupiter's mass, too small to sustain fusion, but formed through the same process as stars. These objects are planets in every sense except origin. They have the mass of planets, the composition of planets, even potentially the moons of planets, but they never orbited a star. They were born alone and remained alone. Some rogue planets might have even more complex histories. They could be captured by stellar systems, orbit for millions of years, then be ejected again. When a rogue planet passes close to a star system, the star's gravity might capture it into a distant, unstable orbit. For a time, the rogue becomes a normal planet, but these captured orbits are rarely permanent. Another close encounter, either with another planet or a passing star, could eject the planet again. A single planet might be captured and ejected multiple times over billions of years, spending periods as a normal planet, interspersed with eons of wandering. It's a cosmic game of gravitational pinball, with planets bouncing between systems. The defining characteristic of rogue planets is darkness. Without a star, there is no day, no seasons, no years, only eternal night. The darkness is absolute. On Earth, even on the darkest night, there's scattered starlight, zodiacal light, airglow. On a rogue planet, without an atmosphere to scatter light, the darkness would be total. The only illumination would be the stars themselves, point sources of light, too distant to illuminate the surface. Standing on a rogue planet, you would see the stars more clearly than from anywhere on Earth. Without atmospheric distortion or light pollution, the Milky Way would blaze across the sky. Other galaxies would be visible to the naked eye. The universe would reveal itself in all its glory. But this cosmic vista would provide no warmth, no energy, no possibility of photosynthesis. The surface temperature of most rogue planets would be barely above absolute zero, perhaps 30 to 50 Kelvin, minus 240 to minus 220 degrees Celsius. At these temperatures, atmospheric gases freeze and fall as snow. Nitrogen ice, oxygen ice, even argon ice would coat the surface. Yet rogue planets aren't necessarily dead. They have internal heat sources that could persist for billions of years. Radioactive decay. Like Earth, rogue planets contain radioactive elements: uranium, thorium, potassium. These elements decay slowly, releasing heat. This radiogenic heating could maintain geological activity for billions of years. Gravitational compression. Large rogue planets slowly compress under their own gravity, converting gravitational potential energy into heat. Jupiter radiates more heat than it receives from the Sun. Due to this process, a rogue Jupiter would still have this internal heat source. Tidal heating. If a rogue planet has large moons, tidal forces could generate heat. As the moon orbits, it flexes the planet, and vice versa, creating friction and heat. This process powers the volcanoes on Jupiter's moon Io, and could work equally well for a rogue planet system. Residual formation heat. Planets form hot. The process of accretion, countless impacts of smaller bodies, generates enormous heat. This primordial heat takes billions of years to radiate away. Young rogue planets could still be warm from their formation. The combination of internal heat and surface ice creates an intriguing possibility. Subsurface oceans. On a rogue planet, the surface would be frozen solid, but beneath that ice, insulated from the cold of space, and warmed by internal heat, liquid water could exist. These oceans could be vast, containing more water than all Earth's oceans combined. The ice ceiling above would be kilometers thick, perhaps tens of kilometers, but below, in eternal darkness, liquid water could slosh in planet-wide seas. The pressure at these depths would be enormous, but water would remain liquid. These oceans would be strange places. No sunlight would ever penetrate. No photosynthesis would be possible. But hydrothermal vents on the ocean floor, powered by the planet's internal heat, could create oases of chemical energy. On Earth, such vents support entire ecosystems independent of sunlight. Could the same happen on rogue planets? Some rogue planets might retain thick hydrogen atmospheres that could trap heat through an extreme greenhouse effect. If a rogue planet formed with or acquired a hydrogen atmosphere thousands of times thicker than Earth's atmosphere, the pressure at the surface could create a powerful greenhouse effect. Hydrogen is excellent at trapping infrared radiation. Even without a star, the planet's internal heat could be trapped, maintaining surface temperatures above the freezing point of water. Recent models suggest that a rogue planet with Earth's mass and a hydrogen atmosphere, just 1%, the mass of the planet could maintain liquid water on its surface for billions of years. The surface would still be dark, but it would be warm, a dark tropical world sailing through the void. Rogue planets are perhaps the most difficult objects to detect in the universe. They emit almost no light. They're small compared to stars, and they could be anywhere. No reflected light. Planets orbiting stars are visible because they reflect starlight. Rogue planets have no star to reflect, minimal thermal emission. Older rogue planets have cooled to near the cosmic background temperature. Their thermal emission is negligible. Small gravitational effects. While rogue planets have gravity, their effect on nearby stars is tiny and transient. They would need to pass very close to a star for us to notice. No predictable location. Planets and systems follow predictable orbits. We know where to look. Rogue planets could be anywhere, moving in any direction. Vast, search space. Space is enormous and mostly empty. The chance of a rogue planet passing through our detection zone at any given moment is infinitesimal. Despite the challenges, we've developed several methods to detect rogue planets. Gravitational microlensing. When a rogue planet passes precisely between us and a distant star, its gravity acts as a lens, briefly brightening the star. These events are rare and unrepeatable, but they reveal otherwise invisible objects. Direct imaging. Young rogue planets, still warm from formation, glow in infrared light. Sensitive infrared telescopes can detect these objects in nearby star-forming regions. Kinematic studies. By studying the motions of stars in young clusters, we can identify objects moving like cluster members, but with planetary masses. Astrometric wobble. If a rogue planet passes near a star, it causes the star to wobble slightly. Future telescopes might detect these wobbles. We've already found several confirmed rogue planets, and many candidates. PSOJ 318.5-2. A rogue planet about 80 light-years from Earth, with 6 times Jupiter's mass. It's young enough to still glow in infrared, allowing direct detection. CFB-DSIR 2149, Midas 0403. Part of a young stellar association, this object has 4 Midas 7 times Jupiter's mass, and shows all the characteristics of a rogue planet. OTS-44, one of the smallest free-floating objects found, with only about 11.5 times Jupiter's mass. It's surrounded by a disk of dust, and might even be forming its own moons. Y0855 Midas 0714. While technically classified as a brown dwarf, this object is only 3 Midas 10 times Jupiter's mass, and could represent the boundary between large rogue planets and small brown dwarfs. MOA 2011 BLG 262, detected through microlensing. This might be a rogue planet with a moon, a planetary system without a star. The number of rogue planets in our galaxy is staggering. Different estimation methods give different numbers, but all agree, rogues vastly outnumber stars. Microlensing surveys. Based on the frequency of microlensing events, astronomers estimate there are at least as many rogue planets as stars in the galaxy. That's 100 Midas 400 billion rogues in the Milky Way alone. Star formation models. Studies of how stars and planets form suggest that for every star 2 Midas 3 planets are ejected during system formation. This would mean 200 Midas 1 200 billion rogues. Direct imaging surveys. Observations of young star-forming regions find numerous free-floating planetary mass objects. Extrapolating these numbers suggests thousands of rogues for every star. The most extreme estimates suggest there could be 100,000 rogue planets for every star in the galaxy. If true, the galaxy contains quadrillions of these wandering worlds. They would be the most common planetary objects in the universe. If rogue planets are so numerous, they represent a vast invisible population. The combined mass of all rogue planets might exceed the mass of all visible stars. The galaxy could be full of dark matter in the form of wandering worlds. This hidden population could explain some astronomical mysteries. Missing mass. Galaxies rotate in ways that suggest more mass than we can see. Some of this dark matter could be rogue planets. Microlensing events. Many microlensing events remain unexplained. Rogue planets could be responsible. Interstellar visitors. Objects like Oumuamua and Borisov. Interstellar objects that passed through our solar system might be debris from rogue planet systems. Counterintuitively, rogue planets might be capable of supporting life. Not life as we typically imagine it, but life nonetheless. The key requirements for life as we know it are liquid water, chemical energy sources, organic compounds, sufficient time for evolution. Rogue planets could potentially provide all of these. Liquid water. Subsurface oceans, maintained by internal heat, could exist for billions of years. Chemical energy. Hydrothermal vents could provide chemical energy through serpentinization and other reactions. Organic compounds. Rogue planets would contain the same elements as other planets: carbon, hydrogen, oxygen, nitrogen, phosphorus, sulfur. Time. Without stellar evolution to worry about, rogue planets could maintain stable conditions for tens of billions of years, far longer than stars remain stable. Life on a rogue planet would be unlike anything on Earth's surface, but might resemble our deep ocean ecosystems. Chemosynthetic base. Without sunlight, ecosystems would depend on chemosynthesis. Bacteria would convert chemical energy from hydrothermal vents into biological energy. Food chains. These bacteria would support larger organisms, perhaps analogues to tube worms, clams, and crustaceans found at Earth's deep-sea vents. Biological light. In eternal darkness, bioluminescence might be common. Life might create its own light for communication, hunting, and mating. Slow metabolism. With limited energy, life would likely be slow-moving and long-lived. Organisms might live for millennia, growing and reproducing very slowly. Global ocean circulation. The entire ocean could be connected, allowing life to spread planet-wide. Unlike Earth's isolated deep-sea vents, a rogue planet's vents might support a global biosphere. Rogue planets could play a crucial role in panspermia, the spread of life between worlds. When a planet is ejected from its system, it might carry life with it. Bacteria frozen in ice, or buried deep in rock, could survive the journey through interstellar space. If the rogue planet later passes through another system, impacts might transfer this life to other worlds. Rogue planets could be vectors for spreading life throughout the galaxy. They're like cosmic seeds, carrying life from system to system over millions of years. A single rogue planet might seed multiple systems as it wanders. This process could even work in reverse. A lifeless rogue planet passing through a system with life might acquire microorganisms through impact ejecta. It could then carry this life to other systems. Rogue planets must occasionally pass through stellar systems. When they do, the effects could range from negligible to catastrophic. Distant passages. Most encounters would be distant. A rogue planet passing through the outer solar system, beyond Neptune, might go completely unnoticed. Its gravitational effect would be minimal, lost in the noise of normal planetary perturbations. Cometary disruption. A rogue passing through the Oort cloud could disturb billions of comets, sending them toward the inner solar system. This could trigger a bombardment lasting millions of years. Planetary perturbation. A close passage could alter planetary orbits. Earth's orbit might become more elliptical, causing extreme climate changes. Mars or Venus could be pushed into different orbits entirely. Satellite disruption. Moons could be stripped from their planets, or have their orbits dramatically altered. Earth's moon, if disturbed, could trigger massive tidal changes. Direct collision. While extremely rare, a rogue planet could collide with a planet in our system. The results would be apocalyptic, the complete destruction of both worlds. Some scientists have proposed that a rogue planet or brown dwarf might be loosely bound to our solar system, orbiting far beyond Neptune. This hypothetical object, sometimes called Nemesis or Planet X, could explain various astronomical anomalies. The orbits of some trans-Neptunian objects seem to be clustered in ways that suggest a massive object's gravitational influence. This could be a large planet in the outer solar system, or it could be a rogue planet temporarily captured into a distant orbit. If such an object exists, it would spend most of its orbit in the darkness beyond the Kuiper belt, invisible to our current telescopes. Only its gravitational effects would betray its presence. Has Earth ever encountered a rogue planet? We can't be certain, but there are intriguing hints. The late heavy bombardment, about 4 billion years ago, the inner solar system experienced intense asteroid and comet impacts. A passing rogue planet disturbing the asteroid belt or Oort cloud could explain this event. Orbital anomalies. The unusual orbits of some solar system objects might result from past gravitational encounters with rogues. Extinction events. Some mass extinctions correlate with increases in impact craters, suggesting comet showers. A rogue planet disturbing the Oort cloud could trigger such events. New telescopes and techniques will revolutionize rogue planet detection. James Webb Space Telescope, JWST's infrared sensitivity, can detect young rogue planets directly, revealing their atmospheric composition and temperature. Nancy Grace, Roman Space Telescope. This telescope will conduct microlensing surveys that could detect thousands of rogue planets. Extremely large telescopes, ground-based telescopes with 30-40-meter mirrors, will be able to image rogue planets directly. LIGO and LISA, gravitational wave detectors, might sense close passages of rogue planets through our solar system. Gaia mission. By precisely measuring star positions, Gaia might detect the gravitational influence of passing rogues. Future missions might even visit rogue planets. Flyby missions.
If a rogue planet passes within a few light years, we could send probes for flyby observations. Gravitational assists. Rogue planets could be used as gravitational slingshots for interstellar missions. Landing missions. Advanced propulsion might allow landing on rogues drilling through ice to explore subsurface oceans. Colony ships. In the far future, rogue planets might serve as stepping stones for interstellar colonization. Rogue planets force us to reconsider what a planet is. The International Astronomical Union defines planets as objects orbiting stars, But rogues challenge this definition. Are rogue planets really planets, or are they a different class of object entirely? The distinction matters for how we understand planetary formation and evolution. The discovery that planets don't need stars reinforces the mediocrity principle, the idea that there's nothing special about our situation. We thought planets needed stars because we orbit one, but rogues show that our configuration is just one possibility among many. Wandering planets might be the norm, and stellar systems, the exception. Rogue planets embody cosmic loneliness. They drift through space alone, cut off from the warmth and light we consider essential. They're reminders of the vast emptiness between stars, yet they also suggest that isolation doesn't mean sterility. Life might exist in their dark oceans. Entire biospheres could thrive in eternal night. Loneliness doesn't preclude complexity or beauty. I first learned about rogue planets through a throwaway line in a science fiction novel. The author mentioned planets wandering between stars, and I assumed it was fictional convenience. Planets need stars. Everyone knows that. But curiosity led me to research, and I discovered rogues were real, not just possible, but common, maybe even dominant. The universe was fuller and stranger than I'd imagined. Rogue planets provide ultimate cosmic perspective. We worry about Earth's problems, but entire worlds drift through space without even starlight. Our concerns seem trivial compared to the challenges life would face on a rogue, yet rogues also inspire hope. If life could exist in such extreme conditions, it might be more resilient than we imagine. Life might not need the perfect conditions we enjoy. It might just need enough. Knowing about rogue planets changes how I see the night sky. The darkness between stars isn't empty. It's full of invisible worlds. Every patch of darkness might hide a dozen rogues, 100, 1,000. The night sky becomes three-dimensional, not just points of light at various distances, but invisible masses filling the spaces between. The galaxy isn't just stars, it's wandering worlds we can't see. Could rogue planets contribute significantly to dark matter? We know dark matter exists from gravitational effects, but we don't know what it is. Billions of rogue planets would have gravity but emit virtually no light. Most physicists think dark matter is exotic particles, not ordinary matter like planets, but rogues could still contribute. The darkest matter might be the most ordinary, just planets without stars. How can objects with planetary mass form independently like stars? The Standard Model says collapsing gas clouds fragment down to about Jupiter's mass, but no smaller. Yet we find free-floating objects with less mass than that. Do these objects form differently than we thought? Is there a mechanism we don't understand? Or are all small rogues ejected planets not independently formed objects? Can rogue planets have moons? Some models say yes. Moons could remain bound during ejection, or rogues could capture passing objects. But we've never confirmed a moon around a rogue. If rogues can have moons, they become even more Earth-like. Tidal heating from moons could warm subsurface oceans. Moons might even have their own subsurface oceans. A rogue planet system could be as complex as any stellar system. Rogue planets multiply the possible abodes for life by thousands or millions. If life can exist on rogues, the galaxy might teem with dark biospheres we'll never detect. We search for signals from civilizations around stars. But what if most life exists on rogues? What if we're looking in the wrong places? What if the galaxy is full of life, but it's all hiding in the dark? In 5 billion years the sun will die. But before that, interactions with passing stars could eject Earth from the solar system. We could become a rogue planet, carrying Earth's biosphere into interstellar space. Would life survive? Deep-sea ecosystems might persist for millions of years, powered by radioactive decay. Humanity, if we still exist, might burrow deep, creating artificial suns and vast caverns. Earth could wander the galaxy for billions of years, carrying life in its frozen heart.